Now, how are deadlocks handled? Well, we will be studying different ways, 3 different ways of handling deadlocks. One is deadlock prevention, and the other is deadlock avoidance. So both deadlock prevention and avoidance, they just do not allow a deadlock to happen. The third method is allowing a deadlock to happen, but recovering from a deadlock. So deadlock recovery. You still allow it to happen, but you have a way of recovering from a deadlock. And the fourth way of handling deadlocks is just do nothing, ignore a deadlock, and which is in fact what most operating systems do. Operating systems do not resolve deadlocks; they leave it to the application programmers. So, analyzing process dependencies and whether we have a deadlock or not, it's the responsibility of the application programmer. The operating systems do not do this for the application programmer. Okay, so how many people ran into a deadlock in assignment 1 or 2? How many people ran into a deadlock? Nobody ran into a deadlock?
I might have, but I probably didn't know what was going on in the code at the time.
So when the program hangs.
Definitely did, yeah.
Yeah, so when you forget one of those set in and get in, set out and get out, this is what, in fact, you will learn more if you run into a deadlock when you are doing the assignment, because you know that there's a problem there. So when you ran into a deadlock, did the system help?
No, it just...
No.
Yeah, did you get like an error message that you have a deadlock or something? It's very silent. You are on your own. You have to resolve this problem. So the system does not detect deadlock. So here in this chapter, we study deadlocks, we analyze them so that we can avoid them, and we can avoid writing code that involves deadlocks. But it's not something that we expect the system to do for us. Okay, so deadlock prevention. So what deadlock prevention is, basically, in theory, we can prevent deadlocks if we can prevent one of the 4 necessary conditions for deadlocks. So there are 4 necessary conditions for deadlocks that we have studied. And if we can just prevent one of them, we will have no deadlocks. So we studied mutual exclusion, hold and wait, no preemption, and circular wait. If we can prevent any one of them, there will be no deadlock. We will prevent deadlocks. But the problem is that conceptually we can, or in theory we can, but in practice, it doesn't make a lot of sense. So we will go through them one by one and see why it's not practical to prevent them. For example, mutual exclusion. So preventing mutual exclusion or avoiding mutual exclusion would mean that you will make all resources shareable, that multiple processes can access the resource. But it's something that we just can't do, because some of the resources are by nature non-shareable, like files in write mode. When you write to a file, you cannot have multiple processes writing to the same file at the same time. Only one process can be running. So mutual exclusion is a must here for correct execution. Semaphores by nature are there to ensure mutual exclusion. So we have introduced semaphores and locks to ensure mutual exclusion. So trying to eliminate mutual exclusion or delete it is like defeating the purpose of having a semaphore or a lock in the first place. So it's something that just doesn't make sense to make all resources shareable. Hold and wait. So we have a deadlock if there is a process that is holding some resources and waiting for other resources. Now, what if we force a process to be, either holding or waiting? Like requiring a process to request all the resources that it needs in the very beginning. So in the beginning, we allow it to be waiting because it requests all the resources that it needs. And once it gets all the resources that it needs, it can go ahead and execute. Now, from a practical point of view, this doesn't make much sense because it's a poor utilization of resources. Having the process request all the resources in the beginning and holding the resources for a long time, holding resources that it doesn't need, is impractical, right? So, and may also cause starvation. So in addition to low resource utilization, there is starvation because if a process has all of these resources, other processes may starve. So this is impractical. Normally a process requests a resource when it needs that resource. Then when it's done with the resource, it releases it. So if a process needs, for example, to access a file, it will open a file, it will do a read or a write or whatever, then it will close the file. And or memory. It will allocate memory, and once it's done, it will deallocate memory or free memory, etc. No preemption. Now, as we said in the beginning, if we can make all resources preemptive, we will not have deadlocks. But as we explained, the resource that is handled preemptively by operating systems is the CPU. And it's good. It's a good thing that the CPU is handled preemptively because this will give all processes a fair share of the CPU, and it will not allow one process to occupy the CPU for a long time, and it will ensure responsiveness and all of that, all of these important features that we have studied in CPU scheduling. But this doesn't apply to all resources. As we explained, it doesn't apply to a semaphore. It doesn't make sense to preempt a process from a semaphore. It makes sense to preempt a process from the CPU, but not to preempt a process from a semaphore. Circular loop. Now, in the simple example that we showed for the deadlocks, we had two processes locking resources in a different order. First process locking the first mutex, then locking the second, and the other process locking the second, then the first. Now, we can avoid this kind of deadlock if we force processes to lock resources in the same order. So if we force all processes to lock the first mutex before the second mutex. So we force this process to do the locking of first before second. Now, in this case, will this eliminate the deadlock here? Or prevent the deadlock from happening? In this example. Yeah, it will prevent the deadlock from happening. Because if we force process number 2 to request the first before the second, it will be impossible for one of them to be holding one lock and waiting for the other lock. So this will work in this case. In fact, this is the only deadlock prevention scheme that deadlock prevention scheme that makes sense in practice. If you force processes to request resources in a certain order. Okay, so in this case, it will prevent deadlocks, but this doesn't work all the time. So for example, sometimes you cannot force the processes to request resources in a certain order. Sometimes the order is dictated by what the process is trying to do. So you cannot force it. In this case, yes, because here, basically a process is trying to acquire two different locks, and the order doesn't matter. So we force it to do it in a certain, we force both to do the locking in the same order, and we can prevent deadlocks. But sometimes the order is dictated by what the process is trying to do. And sometimes it will be, things will be more complicated, like this example. This is an example of a transaction that transfers money from one account to another. So there is the from, the source account, and the to, the destination account. And this is a process that transfers money from one account to another, so it needs to lock both accounts. So here it locks the from account before the to account. So it locks the from, then it locks the to, then it does withdraw from the source and deposit it to the destination. Okay. Now, even if we force all processes to do this, even if we force all processes to do the source before the destination, well, it could be that the source of one process is the destination of another process. Like, for example, if transaction 1 transfers money from account A to B, so the source is A and the destination is B. But for transaction 2, the transaction is going in the other direction. The source is B and the destination is A. So in this case, a deadlock may happen. If one process is trying to transfer money from A to B and the other is trying to transfer money from B to A. So it's not always easy, or it's not always possible to make processes request resources in a specific order.